Welcome back, folks, to another installment of physics. Today we're doing chapter 3, vectors. Little hint, you'll see that my background here is basically graph paper. I've mentioned before that graph paper is helpful in general to keep things straight. With vectors, it's helpful even more than usual. With anything vector, it can really help you do graphical solutions. You can make drawings to scale so you have an idea of what the answer should look like, so you know if your calculations are on track. Just strongly suggest using either graphing or engineering pads when you work this out. All right, so the first thing we have to define is what's the difference between a vector and a scalar quantity. So let's put those up there. A scalar, oops, need some ink. A scalar is a quantity that has magnitude and units, usually units, okay, but no direction. For example, speed. You're going 55 miles an hour. That's a scalar. It's not telling you what direction in which you're going 55 miles an hour. Okay, so scalars, magnitude, no direction. Vectors, have magnitude, they have it all. Magnitude, direction, and units. All right, so for example, velocity. Velocity is a vector. The magnitude of velocity is speed. The magnitude of velocity is speed, which is just, how big the vector is. Right? Now, the most basic vector, this parallels what we did when we were looking at displacement, velocity, and acceleration. The displacement vector Right. So this vector represents a change in position. All right, so remember, change, different, opposite. Okay, change in place. So, right here, A is a displacement vector. So, A, I'm using capital here, so I should stay with the uppercase. A with the arrow above it, that's going to be our representation of vector when we're doing handwritten things like this. This represents the length and direction okay, its length and direction of this change in position. Okay, so A represents the magnitude of the change in position, how long it is, and the direction of the change in position. Now, if we take the magnitude of A, and we're going to symbolize that with absolute value signs. So this is the magnitude of A. Okay, so that's how we represent the magnitude of the vector A. Okay, so that's just the length as opposed to length and direction. Now, understand that in your book, I'll write this, they don't use the arrows because remember they use that line, straight line above a letter for average. So vectors are bold-faced. Bold-face. Let me see if I can make a bold-face A here. So, oh, that's pretty bold. Okay, that's an exaggeration, but you get the idea. Okay, it's gonna be much bigger. Okay, but no arrow. Okay, displacement vectors can be represented by giving the magnitude, the length, and the angle from some reference direction. So, let's take our typical two-dimensional. We have east-west, and we have north-south. All right, so north, east, south, west. If we have a vector, I'm going to draw the vector in red here. And we're going to say that this angle right here is 75 degrees. This angle is 15 degrees. Okay, so let's say that the magnitude of this vector is, for example, 10 miles. That's the magnitude. Now, we can pick really any of these four as reference directions. We just need to refer it to something. Typically, E, the east direction, is used as a reference, but definitely not always. All right, that's because it's like the positive x direction. All right, so this vector would be 10 miles, 75 degrees north of east, right? Because it's from the east direction. From the east direction, you're moving northward. All right, the arrow's moving northward. You could also say it's 10 miles at, should put a comma there between the magnitude and the direction, 15 degrees east of north. Okay, so in this situation, it's kind of the opposite, right? It's starting at north and moving toward the east. All right. So they can be expressed as directions like that, but it can also be expressed as just mathematical graph. And the degrees and stuff are the same. It's just Instead of north, south, east, west, we have a plus and minus x and a plus and minus y. And we have our same vector. Or, well, let's do a different one. Doesn't really matter. 1 mile. And it's at, this is, what are we calling this? 60 degrees. 60 degrees. All right, so when you're doing the coordinate system, the XY coordinate system, okay, it's assumed, unless you say something different, that you are measuring counterclockwise from the x-axis. So the value of this vector is going to be 1 mile, 60 degrees. Okay, if the vector was over here, say, at 60 degrees, at 60 degrees from here, it wouldn't be at 60 degrees. All right, it'd be at, you'd be measuring it from here, and that would be 120 degrees. If you measure in the opposite direction, those are considered negative angles. So this one right here would be 1 mile at 180 plus 60, which is 240 degrees. Okay, so displacement vectors, sum up. Displacement vectors they give us the final position in relation to the initial position. Note that in both of these cases that I drew here, whether it's the north, south, east, west, or the mathematical XY, the origin, all right, is where the vector was assumed to start. Okay? Displacement vectors do not tell us the path followed. Okay, so if we sketch that same vector again, okay, that displacement vector change in place going from here to here, that was 1 mile at 60 degrees. And in blue, I'm going to put the actual path. We don't know what that path is. This thing could have started, we know it started here, and we know it ended here. But it could have done this. You know, it could have done anything. We don't have that information. All we know is the starting and ending point. Okay, so displacement is the change in place. Now, we're using displacement vectors as an example, but all vectors behave the same way. Including the ones that we have talked about last week, velocity, acceleration, and ones we will be talking about in the future, like force. Okay, they follow the same rules that we just saw. Okay, that's it for now. This was section 3.1 in your book. The next video will be dealing with manipulating these guys, vector addition and subtraction. All right, see you soon. Bye-bye.